Hello and welcome everyone. Thank you for joining us today for a webinar titled How to Detect Fraud Quicker with AI. My name is Patrick Moran. I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Dr. Ashraf Arthur is a principal security scientist at H2O.ai. And before I hand it over to Ashraf, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. Now, without further ado, I'd like to hand it over to Ashraf.
Thanks, Patrick. Hi, good morning, good evening, and good afternoon, actually, from wherever you guys are joining. Just a bit of information. There is a bit of work that's going on, in front of my house, so you might hear a bit of jackhammer. I really apologize for that. And also because the air quality out here in San Francisco is pretty bad. We have air purifiers running close by, so you might occasionally hear a hum in the background. I apologize for both of it. And having said that, I'll start off. So today's talk essentially is about how to detect fraud quickly. With the idea that you're applying AI to the whole process. So that's essentially what the talk is all about, and I'll be covering a few slides, and I hope you give me enough time to finish up the slides, and then we'll have a quick amount of time, as Patrick had earlier said, that we'll have time for Q&A. A quick introduction. So my name is Ashraf, and I work as a principal security scientist at H2O. My primary area is electronic fraud, network cybersecurity, and malicious behavior broadly. I've been working here for about 4+ years. This tends to be my primary area of research. Something that interests me is trying to identify malicious actors using data. This has been my research for the past 12 years that I've been doing. So having said that, I will quickly go through today's coverage. So in today's coverage, I will look at, or rather, I'll be presenting how transactions actually happen, some fraud basics, and what are why is it that we need to try and identify fraud faster? Or rather, is there a need to try and identify fraud faster? Is going to be like a big question or a big theme that will surround our entire topic that we speak today. Then there are a few areas that we can actually touch upon to try and see how we can speed up the process. Some of the areas actually, one of the area is, of course, in the field of data science itself. And this is specific to feature engineering, models, and so on. The next stage, of course, or the next topic is about engineering. How do you actually get the features to the point of production, and how do you deploy the model? And the final aspect is going to be the business-specific area that we cover. And here you can look at optimizations based off the needs of the business, not necessarily, it might not be necessary for looking at accuracy as a very important thing, but the business needs might actually help you identify how to balance between speed and accuracy in terms of your models and your features. So having said that, I'll quickly jump into how does a transaction fraud, transactions and transaction fraud essentially look like. What you see here is a general diagram of how a transaction gets processed. There is a customer who approaches a merchant, and this merchant could be an online merchant or an in-person merchant. So you could either go into a shop, or you could be shopping online, Amazon.com, eBay, any of these processes. And essentially, when you present your card information, or in this case, it could be any kind of financial instrument that can be used for purchasing or any kind of processing, the merchant tends to take the card and pass it through a POS terminal or any kind of terminal that can actually validate that this card is valid, that this user is valid, and so on. That transaction ends up with the acquirer, who is directly connected to the merchant, gets the card information, and then passes it on to the card network. The card network could be Star, Visa, MasterCard, and if you are globally, if you're globally placed, it could be UCI, any of these payments. And then eventually through the network, the data gets to your issuing bank, who actually issued a credit card. And this essentially is the general pipeline of how payments actually go through. So there are multiple operators across the pipeline. And in this pipeline, the way actually a transaction gets processed is primarily by the card network and the issuing bank. So essentially, these are the entities that try and identify if there is anything, abnormal, anomalous, malicious about the payment that has been presented to them. So what you see in this pipeline is the merchant and the acquirer almost, there is no fraud detection that actually happens here. Nothing necessarily that that's kind of done. And this is essentially the traditional approach. As we go through, we'll kind of identify that there are things that the merchants can do as well. And when the transaction information actually comes to the card network tends to do some basic checks. Is the card, actually issued by our payment processor? Is there an associated fraud with the merchant? There are some fraud management tools as well that they provide to large merchants or even small merchants, depending on what kind of, what is the volumes of or what is the value of the payment that you process. And then they also provide opportunities to do batch transaction check, where some merchants who, like for example, Target, could actually take up all their transactions, move it at the end of the day, and they get processed. The issuing bank has some basic checks as well. They do some address check. They do whether the amount that you are requesting from your account is actually available, and there is some remaining balance. They do some checks for the CVV, which is basically your PIN, the one that you enter when you're doing a transaction. Then there is a transaction rate check, and then there's a transaction volume check. Transaction rate check and transaction value check are actually pretty simple checks that the issuing bank does. If you tend to do, like let's say, a $10, $20, $50 transaction in a very quick span of time, let's say 30 minutes, then the issuing bank actually raises up a flag, and you could get a message on your phone saying, hey, was it you who actually did these transactions? And these transaction banks could also, or issuing banks could also have transaction volume checks, where they check across a period of time. It could be 24 hours, or it could be, like, let's say, a span of an hour or a span of 6 hours, or, the daytime between 95, if you are actually transacting beyond a certain value, or if it's below a certain value. Sometimes there are different kinds of checks that are also established for transactions that come in the middle of the night, because it's not necessarily something that they see. So these are some basic checks that they do, and then they classify the transactions. And the transaction is very simply classified as fraud or not fraud. Now, essentially, this is where the whole fraudulent or the fraudulent transaction detection does not end. What actually happens is there are two parts in the whole fraud analysis that is actually done. One is the real time, where the processor and the issuer do some basic checks to see that the process of the transaction itself is not fraudulent, and then there is some post-fraudulent analysis. In the real time, as I said earlier, the card check, the CVV check, there are some merchant side signals that I look for. Address verification is also something that they look for. Transaction rate and volume are some of the real-time checks that they do. But there is also a post-transaction fraud analysis that is done. Some transactions, if it's of high value, if it's, if it has been flagged as abnormal, tends to get parked, and then, they have manual, people who can manually check these transactions to see if this is actually valid. Sometimes you might also get a phone call, sometimes you might just get an SMS. Sometimes you might get an SMS and an email. Any of these means to basically check that the transaction that you did was indeed by you or by someone whom you had authorized and not necessarily fraudulent. There are other inputs as well. There is customer feedback, where you as a customer can actually, frequently go into your account and check for certain transactions. And if a certain transaction is fraudulent, you can actually mark it and you can let the bank know. If you see if you see your transactions, you would see that some transactions have been temporarily approved, some transactions have been confirmed, and that essentially is the difference between some of them that are still in the pipeline, some of them that have actually been processed. So these systems also provide a feedback mechanism for the merchant, and this essentially goes back to the processor, where the merchant can actually say that, hey, I think the person whom I saw was not necessarily this person, because I've seen this person multiple times using his card, and the person who got the card today was not the same person. Those kind of feedbacks are also possible from the merchants as well. Then there are some post-transaction models as well, where these models try and identify based off geography, based off the rate, based off the speed of travel, as in the speed of successive transactions, if this was actually fraudulent or not. And this essentially gets passed on to manual investigators as well to try and verify if this actually makes sense. So simply put, the payment processors and the issuing banks are actually able to very quickly provide a decision whether if the transaction is fraud or not by keeping the model very simple. They don't complicate the model. The model is not super bulky. There are not hundreds of features that is actually trying and making this decision. There are very simple things that they look for. Is the card in the system? Is the card present? Not present? Is there a CVV? Does the merchant have like a history of having fraudulent transactions? Can the address be verified? Is the amount available? Was this within a 24-hour rate limit? And this is, by the way, an example. As I said, there might be different billings that might happen. 24 hours might be one, 6 hours might be one, daytime, nighttime might be one. And they could also look for transaction amounts. A lot of they keep the process simple, but you also have to understand that a lot of these systems are based off trust. There is a lot of trust that actually exists across the entire pipeline, and which helps, try and identify fraudulent transactions from non-fraudulent transactions. So that essentially makes this fast and like super usable. I think there is research to say, if a transaction doesn't necessarily happen in a span of like half a second, or I think it's 0.2 seconds, then the customer might not actually come back and want to buy the same product. I think these are some studies that tend to go on, which try and identify, what is the best amount of time that we can have to make sure that the transaction passes through. And these kind of studies are frequently done by payment processors to try and keep up the pipeline, so that they don't necessarily clog up the system with things that they think are fraudulent, but not necessarily so. Now, of course, there are things changing, and for multiple reasons, and I'll come to that very soon. What essentially we are looking for is approaches where we can actually move these fraud detection to be much more faster, but much more comprehensive. So essentially what you would try to do is have more confirming analysis in real time or near real time, rather than have much more analysis, post-transaction. So essentially you could have things like, apart from the ones that I said, like card checks, merchant checks, address checks, and transaction rate checks, you can also have like longitudinal analysis on transaction data. You can have like seasonal analysis. You can have like population analysis. You can throw the entire kitchen sink of feature engineering onto this and you would get a fantastic model. But I think the thing that you have to balance is between how comprehensive your model is going to be and how fast you would you actually process these payments. When you do that, on the post-transaction fraud analysis, you would actually have smaller number of path transactions. There are smaller number of transactions that needs to be analyzed, but still there are pipelines open for customer feedback and merchant feedback. So that essentially, provides you the value that you are able to confirm a lot more transactions quickly in real time or near real time than actually passing transactions and doing the whole process later on, which essentially could be costly as well. Because every time there is a payback or a chargeback in this case, the bank has to go through a process, the payment processor has to go through a process, and sometimes the acquirer also has to go through a process depending on the kind of agreements that they have. A simple illustration about how these systems work, and a lot of these current systems that that are there, that are at least making the decisions are heavily rule-based. So very simply, this is a very simple representation of how the rule-based systems are actually making a decision. Is there a CVV or not? Then deny or accept. It's a very simple model. It's very fast, very basic features. Unfortunately, the thing that they lack is the ability to adapt. Is something that they lack, which essentially means that there is a lot of re-engineering effort that actually goes on when these rules needs to be changed. And why is it that adaptability is a big thing? I think one of the things that we do see across the board is that fraudsters don't necessarily stop when their transactions are actually prevented or stopped by the processor or the issuing bank. They actually identify new techniques to try and defraud the whole system. So essentially, you can look at this as a cat and mouse game, which essentially means that you step up and then they step up too, and then that kind of goes on. It's very cyclic. When you look at an ML-based model, if you were to directly apply the ML-based model, maybe this picture doesn't illustrate the exact complexity of an ML model, but just for simplicity purposes, an illustration of kept it simple. The models can be very comprehensive. They can be comparatively slow to the rule-based engines, but it does have a rich set of features. And one of the biggest advantages is that it's heavily adaptable. There are things that these models can identify that simple rule-based engines would not necessarily try and identify. Now the thing is, to try and get models like this to operate in near real time is the biggest challenge I think a lot of people face, or a lot of institutions for that matter face. And then that's where some simple ideas kind of help assist us with the whole process. But of course, I think the big question always is, why is it that we need to have faster detection, right? I mean, it's fine. Like, I think if I'm right, Visa has a theoretical throughput of about 65,000 transactions per second. I think one of the largest payment processors that's based out of Asia, I think, has a throughput close to about, I think, 30,000 or 40,000 transactions per second. But they don't necessarily fill up these, these pipelines. I think Visa, at its peak, tends to transact about 2,000, maybe 1,700 transactions per second, and some of the largest payment processors out in India tend to transact about, or Asia for that matter, tend to transact about 10,000 transactions or about 12,000 transactions per second. So you're not necessarily filling up the pipeline. But why is this actually so important? The online purchase is on the rise. You have a lot more people, purchasing by electronic monetary instruments or digital cash for that matter than physical cash, which essentially means that the medium of transaction processing is primarily going to be electronic, which essentially means that fraud detection also has to grow with the same increase in transactions. there has been, I think, quite a bit of research. I think there are some references out on the slide as well, where, post-COVID, in the year 2020, a lot of transaction spikes or repeated transaction spikes have kind of mirrored the Black Friday sales, which is essentially very interesting because, Black Friday sales tend to be this one anomalous big blob of data that people tend to see across an entire year. And this has happened routinely multiple times in the year 2020. So if transactions move online, and if you kind of see this kind of spike, then it is imperative that your fraudulent engine, fraud detection engines for that matter, can actually detect things at line speed and faster. And in non-COVID years itself, fraud has increased by about 25%. I think card not present fraud, where you're not necessarily present in physical card, usually in stores, has actually increased by about 81%. So you can kind of imagine how much a fraud increase can actually happen when everybody is probably home and shopping from home and so on. So these are essentially some of the reasons why we put out saying that it is important for the fraud engines to be much more faster, so that they can be a lot more valuable in terms of differentiating between a right transaction and a fraudulent transaction. So how do we move our systems, current systems for that matter, which have comprehensive models? How do we make them faster? Like, what are the things that we can actually do? One of the first things that we can attack, or for that matter we can approach, is the data science part of it itself, which is one of the fundamental things that we can look at. And under the data science, the first thing I would like to capture is the feature engineering part of it. So building a comprehensive feature set is great. It's super good because you'd have a super high accuracy. You'd probably reduce your fraud heavily compared to what you were facing, but it might not necessarily be so valuable when it goes into production if it's actually slower. As I said earlier, if your fraud processing time takes about close to about half a second or 1 second, the customer might actually lose interest in sending the payment repeatedly in case, let's say, you classify it as fraud. So what you have to balance what you do have to balance is the number of features you put in, the type of features, and the complexity of the features. And what I mean by that is you can actually use many different kinds of features that add value, but when you're running a fraud, essentially your processing is a function of time. It's very important to try and see if you can apply zero prior knowledge features. And of course, this is a value-based system where if having no prior knowledge actually is valuable enough for you to predict, then that's a good way to go. But that's a good way to go. But if not, you can switch over to many different types of features that actually add value, but you can do some modifications there as well. So if the signals from individual records, individual transaction records are strong, then avoid features that are a function of time. Like look at the data longitudinally, or comparing individuals to different populations. For example, you could transactions. While you're evaluating transactions, you could look at different homogeneous families. You could look at this geographically. You could look at this by the transaction value evaluation, or you can look at this by the type of product that you buy. And these could actually add some amount of time to the entire process pipeline. And if this is something that you can avoid by using the basic data set that actually comes in to your system, then that's great. So let's say you cannot. Let's say it is important for you to actually have some functionality of time or a longitudinal evaluation of your data or family of features. Then it is important to actually keep those things very crisp. You can keep your historical data a bit small and your reference population small as well, but make sure that it is always relevant. And what do I mean by relevant? For example, a lot of feature models that I've, a lot of models that I've actually built, my go-to used to be, looking at historical periods for like a year, 2 years, 6 months, 3 months, 15 days, and so on. But if in your data, and this requires a bit of EDA, right? So when you do a bit of exploratory data analysis, you would actually see that your transactional behavior tends to have a certain pattern, okay? And if the pattern tends to be very similar, and in this case, I don't need to look at historical transactions across a 12-month period, while I can probably capture the same thing over a 3-month period. And that's essentially the shift that you can do. When you shift from a 12-month period to a 3-month period, you're reducing the amount of computing time. Essentially, you're reducing the time that it takes to actually identify whether the transaction is fraudulent or not. A very simple difference, but it actually gives us a lot of value in terms of the time that we save. And the next thing that I want to switch to is the modeling part of it. Of course, the feature engineering doesn't necessarily, add any value if you don't have a good model to it, right? So if you try and keep your model as simple and as effective, and that can be, like the fastest that you can actually have. If you have a simple model with a good accuracy and a comprehensive model with a better accuracy, then your choice. It might be a wise choice to actually go with the simple model, depending on how good your accuracy score is. Primarily because your speed is much better compared to the comprehensive model. And while detecting frauds in volumes, speed is actually much better in your return than looking at accuracy as well. If much of your transactions are like, let's say, in a small bucket, if you were to do like a histogram of your transactions, and if much of your transactions tend to be in a small zone, then it's much better to look at things by volume rather than actually try and identify mark each and every individual transaction. Don't essentially make your models very complex. If your fraud is detectable by a GLM model, a very simple model, then use it. I mean, it makes no sense to have a complicated, neural network model for something that you can actually identify by GLM. It just does not make sense when you have to. I mean, the problem actually tends to become much more complex, or tends to be amplified when you actually try to take that model into production. So if you have a simple model, apply it. It's easier to build, it's easier to predict, and it's easier to put it into production. So essentially, that gives you, and something that's really easy to achieve the goal that you want. And essentially, having a simple model also makes it easy for you to like retrain, reconfigure, and then put the model back in. You don't have to necessarily make your models unnecessarily deep. And if you tend to have a lot of categorical features, factorize, or in this case, encode your data. It actually it provides a lot of value when you like encode your data. It tends to make things faster. One of the other aspects that I've seen across the groups and the teams and the customers that we've worked with, of course, this was the initial years, where one model can be considered as a great model, and that essentially, tends to get applied. That's not necessarily the case. Models have been heavily commoditized. So essentially, for you to churn out n number of models, 100 models, is much more easy than it was, like, let's say, 2 years ago, 4 years ago, or any of those things. So if you are in a situation where you can use multiple models, great, then go ahead and use that. I mean, it helps you break down your problem into multiple small problems, and you can probably run them in parallel. If you can break down your data, across heterogeneous groups, then use that to your advantage. Create models for like independent groups, use forms like segmentation, transaction types, transaction amount binning, and so on. I mean, these are just examples, by the way. For example, let's say you're looking at transactions that come into your system, and you have transaction types where there is like a cash transfer, and then there is like a purchase. It actually behooves that you have separate models for these two, because the feature set that goes into each of these models can be crisp and can be small, which essentially makes your scoring faster, which essentially makes your entire system and the institution much better in identifying fraud than having one comprehensive model that tries and identifies these things. So creating these strong segments are actually very valuable. And mind you, when I talk about segmentation, these are things that you can actually see in the data. These are clear lines that you can draw within your data and say, this is something that I can make a separate model for, and this essentially works out great. You can also make very simple differentiation in your data when, like, let's say, when a card is not present or when a card is present. And essentially, when you break this down, you can have very simple models, or let's say one simple model and one a bit more complex model, and that essentially kind of divides the pipeline and tends to give you a much better advantage in terms of speed. You could probably capture much higher rate, not just the transaction pipeline rate, but your decision rate could also be very high because you're kind of parallelizing these two while giving them two separate models. And for example, let's say you have features. Let's say there are aspects where you cannot necessarily draw a line between your data set, or you cannot necessarily perfectly segment your data set. The example that I gave earlier, where it's between a cash transaction and a cash transfer or a purchase, or a card not present and card present, are actually very distinct lines that you can draw in your data set. Sometimes you might not have, you might not have the luxury of doing that. In those times, you can look at your transaction amounts. As a financial institution or as a payment processor, you could be dealing with different transaction amounts. And essentially, here is an example of how your transaction amount histograms could look like. One of the institutions that we had worked with tended to have kind of a lot more, smaller amount of transactions and much less larger amount of transactions. And I believe this is kind of the case all across the board. It's not necessarily very different. Then what you could do is you could bin them. You could make them separate, and you could have specific models for identifying, transaction values that are actually smaller, and a separate model for actually transaction values that are higher, transaction values that are much higher. And this would give you, the edge as well in terms of speed of how you can process your payment, try and provide the decision very quickly. Of course, so in these examples, I speak about two different kinds. One is where, you can break your data down very clearly, and in certain areas where you cannot necessarily break your data down, so you have to apply some statistical approaches where you can look at the distribution and then say, okay, you know what, this is a good point of demarcation where I can separate the data and actually build these models. The next thing that I actually want to talk about is something where there is something that's actually pretty new. I wouldn't say very new. I mean, it's been there for the past 10 years, but I think it's gained kind of traction much better now. There are integrated payment systems through which you can use your secondary signals. Some of these integrated payment systems are like Apple Pay, Amazon Pay, PayPal, Visa checkout, direct bank payments, and all of these things, right? Where essentially what's happening is you have, let's say, a small web pop-up. I think PayPal does that. Or you can have a small, like an iframe that comes out in a web page where you say, enter your card information here and we'll process it through this way. So essentially what's happening is, the space between the customer and the merchant payment processor and bank has kind of reduced. So everybody is able to talk, all of these guys, the merchants, the payment processors and the banks are able to kind of directly talk to the customer. And when I say directly talk, I don't mean like, have a conversation. I mean, they are able to have their individual models, individual systems to actually make checks that can actually add value to them. You can go ahead and use these signals that actually come through from these interactions and try and identify if something seems fraudulent. For example, very simple secondary signals that we've implemented. The IP addresses of the purchasing machine and the secondary device, and associate the secondary device. It could be a phone or a laptop. In case you're purchasing through a phone, it could be a laptop. The IP addresses is the same. Does the location look, is there a match in the location between these devices? How old is the merchant session, for that matter? And the length of the merchant session essentially is a very valuable thing, because if I was going to do fraudulent transactions, then I would essentially be switching in accounts or credit cards very quickly. I would be changing this very quickly to see how quickly can I draw all the money out of all these list of cards that I've bought by malicious means. So the merchant session essentially gives you the confidence that this is a customer who has kind of been here for a long time, hasn't necessarily changed the card and so on. Or you could also look at how many sessions has this device had. For example, let's say I'm like a retailer similar to Amazon. I could be looking at how many different sessions have I had in this device in a given span of time. I think most of us probably tend to have like one session maybe across a week, unless the session gets reset. And this could actually add value, like a secondary signal to tell you whether this is like a good transaction, or could it be fraudulent, or could it be suspicious, for that matter. And what are the types of buys that actually happened? Is this something that came from the wish list, or was this an instant buy? Was there any search before they actually bought this device or bought this product, and so on? And this could actually assist you in trying and identifying, whether of course this is fraudulent or not. And these are very simple features, and this is essentially just true or false, which if you look at it, is no different than the very simple decisions, the rule-based decisions that actually payment processors and banks actually currently make. So it keeps the model very simple, keeps it light, which essentially means that you again gain speed. So these are like some of the advantages that you can use if you work with some of these integrated processors or integrated payment systems. So having moved on from like data science, I would like to switch to the engineering part. There are some optimizations, or there are some customizations that you can kind of do on the engineering part as well. For example, you can actually pre-calculate some of the features and keep them ready. You don't have to dynamically calculate, like, for example, a risk scores of gas stations all the time. You can geographically bucket them, you can calculate the risk scores and keep them ready, and as and when a transaction from a certain geographic location comes in, you can append the risk score with it and push it forward for the model. And geographical risk scores are not necessarily dynamic. They don't change very frequently, so you can update them periodically. It could be like every let's say 15 days, a week, a month, 6 months. I know some of the institutions that haven't changed these scores for like 2 years because it just doesn't make sense for them to change it. And so you can keep these things ready, which gets appended to your data set before it gets scored. You can also make things like geographical transaction value risk. What is the kind of transaction that's actually coming here? Is it more risky? Not. You can look at segment transaction value risk. Which essentially means that what is the kind of, let's say, if you're looking at retail, what is the kind of product segment am I looking at? Am I looking at like groceries? Am I looking at like simple, needs of the house? Or am I looking at like a fancy new television or a new stereo system and so on? Or a new Apple computer. I think that's one of the things that they shoot for. I think fraudsters tend to do this. They tend to get the smallest product for the most value that can be sold very easily as well. So that's kind of the thing that they hit. So you can use you can kind of bucket them as well to kind of create a segment transaction value risk, and then use that in your model as well. You can look at things seasonally as well. When around a year, when around a day, do people tend to make much more fraudulent transactions, and you can associate a value for that. So time of day is essentially that. Night transactions can be a bit more riskier, much more impulsive than transactions in the day. So these are values that you can actually have preset, and you can add them. And in terms of the feature engineering as well, some of the fast type features you can look at are like factors, factorize encode. You can use booleans, you can use integers. If you don't necessarily have to have a long string if it's got a high frequency of occurrence. Just encode it. It's very simple. So one of the things that I also want to switch to is the modeling aspect of engineering, right? So models, of course, as I said earlier, have been commoditized. So you can use many of them. You can create many of them very quickly, and you can parallelize them. You can use them together. You literally don't gain anything if you make one model and say this is my best model. I think model has become very iterative. You can create meta models, use location-based data to calculate risk, and then use that information to feed to another model. You can also use transaction amount as a risk predictor. You can use outcomes of multiple models to a final predictive model, which essentially makes it very easy. So you can run this location, transaction, and all of these things in parallel, and finally send it to one final model, which makes your transaction validation or invalidation really fast. And some of the ways that you can look for, so when you parallelize the models, you can run through multiple models. I mean, here you see an example of me running the same transaction through multiple models specifically for purchase. These are all sub-models. And then you can use a simple weighted approach. You can use the highest scorer. You can elect it, at any given point in time to see which model actually ends up being valuable. So we've discussed the data science part of it. We've discussed the engineering part of it. But one of the fundamental things that we as data scientists should be very wary of is also what is the needs of the business? Like, what is it that they want us to do when we are building these models? Getting an accuracy of 0.99, but a model taking like 5 seconds to score is not something that the business would be comfortable with. I mean, once you explain this to them, I think they might come back and say, you know what, reducing the score is much better than having reducing the score and having a faster model is much better than actually having a highly accurate and a slow model. So build models that are fast and accurate, and in that order, of course, not just accurate. And you also have to make decisions based off risk. This is where I think your business risk team is a very good group to actually interact with. So for example, if you're looking at transactions, right? Like, does it make sense for you to like solve hundreds of like $50 transaction, or does it make sense to like identify one $50 transaction, right? Your institutional risk team might be able to help you, and as a data science team that you lead, you could also learn from them. The model, and because of your data size as well, because you see more and more $50 transactions or like less value transactions, you might be able to learn much better in that group, which means that your risk in that segment or in that bucket or in that bin would be much lesser compared to the risk associated with the $50. But of course, the $50 transaction is single, so you can offset that with essentially having much more speed. And so kind of see what the wise choice is. And I'll give you a very simple example. Like, let's say model A, and this is something that we've implemented, and I can kind of go through this example, where we have seen, like, model A uses about like very simple 4 features and gives an accuracy about 0.9. It's fast. While model B has about 27 features. We had a lift of about like 0.02, which essentially was a good thing. But it was like 0.2 seconds slower. How would you actually rate it? In this case, we kind of ran the test between both of these to see which model was actually more valuable. Like, did a customer have any effect based on which model was actually present to them? So that was kind of useful. So in this case, which one would you use? Like how would your business actually weigh in? Like what would they say when you run one of these models or when you run the other one, for that matter? So having said these, I've covered like most of it. I quickly wanted to jump, as a reminder as to why we need faster detection. Because of, our current processing times are at a certain rate, which essentially means that we need to up our game in terms of fraud detection. Online purchases, more transactions are going to be there, because of COVID as well, I think the transaction volumes tend to increase as well. And of course, because fraud tends to increase as well. Fraud actually is increasing year by year because a lot of payments are actually moving to digital, so that tends to kind of add the burden on us. But that does not mean that we kind of weigh down because of the burden. There are lots of techniques, as I've spoken about earlier, which you can adopt to kind of offset and improve the speed rather than get into a comprehensive model that can be much more slower. And then, simple conclusion, what I do want to say is the kind of things that we hit in terms of the data science, you can look at feature engineering. Small number of features are great. If you have a crisp, small, longitudinal, populational, data. In terms of the modeling, keep the modeling simple if you can, as simple as you can. Rather, that's a better way of putting it. Segment your data set, bin your data set that helps. Use secondary signals. I have had amazing success by using secondary signals. I think the only thing that's needed for secondary signals is your data must have those things, and I think that is where the value is. But secondary signals are super valuable, and I've seen a lot of value that have come out of these signals. In terms of engineering, you can always pre-calculate, you can always encode. In the models, you can use multiple models. You can use many different model designs, like meta models and parallel models. And when it comes to business, always try and see what is it that the business seeks, how is it that they plan to offset the risk, and that might actually give you, the approach that you want to take when you're building your model across your data science teams. Having said that, I think. Patrick, we can probably open it up for discussion. I just wanted to run through, if any one of you have these problems where, what are the problems that you're facing with your fraud engine? Are you fast enough? Are you slow? How are you placed in terms of accuracy? Or do you even lack data, to make these much more broader decisions about how to optimize your data set and so on? Any other questions and comments, gladly welcome.
Sure. So everybody please start typing in your questions. We'll be answering all of them with time permitting. First question here is, how would you identify anomalies, as there will be huge transactions ranging in the transaction amounts, right?
Fair enough. So there are many different ways that you can look at anomalies. And of course, I think I would want to ask you if it's possible, whether is it dependent, are you looking at it, are you wanting to be fast, or you just want to try and identify anomalies? One of the simplest ways that I've seen across the years I've worked in, in the area of trying and identifying anomalies is that a simple distribution and looking at the data set after the distribution, like plotting it out, actually gives a lot of value in trying and identifying where your anomalies might look like. The only thing that you need is that you need to be able to project the data set so that your anomaly is actually visible. So distributions add a lot of value. If you tend to have a bit more amount of time, variable clustering is one of the mechanisms that you can actually use, where you can look at your anomaly as to how far is it from any of the clusters that actually exist. You can also look at things like, I think, isolation forest is one of the new approaches that is that seems to be very valuable in terms of anomaly detection. But of course, it's got the one small area of where you have to say how much of anomalies do you look for. But I would still say if speed is important, looking at there is nothing second to looking at the distribution of the data.
Okay, great. This one is referring to slide 17. It's asking, what is the ROI on slide 17?
Okay, I can speak about the ROI. So in terms of return, the return is actually what you're looking for is the risk to reward ratio, if I can place it. In terms of what is the value that you're getting if you were to, like, let's say, increase the amount of time or decrease, if you're to remove a certain feature set and so on. So essentially, you're looking at what is the cost to my institution if I were to allow this transaction to actually go through, or if I, ban this transaction, or if I prevented this transaction from going through. And some of these inputs, some of the returns, as a data scientist, I think for us, ROI doesn't necessarily bring in so much of a value unless we get this from the business. Like, they need to be able to tell us, what is the risk that we're able to take, what is the risk that we're able to fathom, and what is the risk that is not possible. So your return would actually depend on the risk value that is associated with your institution, or for that matter, that kind of a transaction.
All right, and just as a general reminder, the slide deck will be made available after the presentation is over. The next question is asking, so what do you mean by encode the data?
Great question. So very simply put, if you have like, let's say, simple strings that are essentially, high frequency occurring strings that are there in your data set, you don't necessarily have to use those strings. You can actually encode them into simple integers. If you have, like, let's say, just two different strings that occur at different frequencies, so you can re-encode them as binaries, just like 0 and 1. If you have three strings, then you can do the -1, 0, and 1. So you can basically transform anything that's a factor, or anything that's, I think, the categorical variable, into an integer, which tends to make it, which tends to help your processing, which tends to help reduce your processing time. So that's essentially what the whole encoding process is about.
Okay. So this question is saying, it was clear that secondary signals have been extremely valuable. Can you be more specific as to what those were? Where you want to get them, or sorry, what those were, where you went to get them, and how you structured them? Were they all Booleans, for example?
So the set of secondary signals that I've actually shown you are all Booleans, which kind of makes it really easy to to use the data for your modeling. Now the thing is, there are a set of secondary signals that you can also use, which are not necessarily Boolean, which are probably a bit more complex. And the way you basically get them, I think this goes more to how these integrated payment systems have been integrated into the merchants itself. I think when you go online and you try to shop, there are these options where you can use the Visa checkout, you can use like PayPal, you can use any of these payment options, right? And when you use these approaches, those systems can also see the kind of information that probably a merchant would see. Very simply put, you can see the IP address, you can see the location, you can see like a session information, you can see any of those things, those information. So if you are, like, let's say, an integrated payment system, which essentially what would happen is a payment processor didn't necessarily see the original, like, the kind of information that a merchant could see, but using these but because now we are integrated, you can see the same kind of information that a merchant can see as well. So in your transaction, you would be able to get this data set. And that's essentially what you would use to build up your secondary signal data set.
Great. In fraud detection, how do you achieve optimization between false negatives and false positives, as one can be dangerous and the other can be costly to process if their count raises?
Of course. I think that's probably one of the most fantastic questions that I've heard today. One of the big things that you do have to do is, this is where I think inputs from your business comes in. As a data scientist, we cannot decide false negatives, for example, false positives and false negatives, or true positives for that matter even, in vacuum. We do have to see what is the risk associated with each of these groups. I mean, there are 4 separate groups that you actually have, right? So a low amount of false positives is always great, because it helps you process much more, but you do have to try and identify the risk that is associated with it. If you primarily transact, like, let's say, transaction values between $10 and $100, and much of your false positives are actually in that group, well, then you kind of have to tune your model to say, you know what, I'm going to be much more better in this group rather than in the other group. Because remember, your primary transactional group is between the $10 to $100, which essentially means that you're losing value by risk. I mean, you're losing whatever, remuneration or any of those things by volumes. So you should try and avoid that. If your risk is coming from a segment which is not necessarily, very largely used, then you can always have an associated risk with it and say, this is an offset that I can actually take. And this is where that interaction with your business actually becomes very valuable to say, what is the risk associated with each of these segments? What is the risk that we can take? What is the risk that we can't take? And then you can tune the knobs and, reduce your false positives, false negatives for that matter.
Great. We have a very highly imbalanced data set with very few transactions in the target population. What are some techniques to help identify future targets?
Okay. So if you have a highly imbalanced data set, I would suggest that the first thing that you do is look at the distribution. Look at where try and project your data set in such a way that you can actually look at the distribution, where you can try and identify, the fraudulent transactions that are actually coming in. So that, I would say, is one of the fundamental ways of trying to look at your data set. Having done that, you can actually improve the weights. For example, if you're not looking at the whole data set longitudinally, then you can oversample and then you can improve your model. But if there are some features that are looking at things longitudinally, essentially you are applying a function of time to a data set, then oversampling doesn't necessarily work. It'll actually hinder the process. So in that case, you can actually use weighted techniques to try and identify them much better than, like, let's say, the other group. But distribution and then using weights, if it's longitudinal, distribution and oversampling if you're not looking at any function of time in your data set. That would be the approach I would say.
Great. All right. I think this is going to be our last question. Do you have any specific advice or special consideration about how to track and prevent fraud related to direct debit and ATM reference payment methods?
So actually, that's I think that probably is a good question as well. The thing that comes up with this is much more closer to the issuing bank, or in this case, the final organization that actually looks at the transaction, or rather, who owns the card itself. What I would suggest is having a mechanism where you have a simple model, but a much more feedback in terms of interaction from the customer will probably be valuable. Because remember, direct debit is something that's actually is actually increasing in its numbers. So essentially, you could build basically an initial model with some amount of customer feedback, and then use that to bootstrap models where you don't necessarily need customer feedback. And that would essentially be probably an approach that I would take. Great.
Thank you, Ashrit, for taking the time today and doing a great presentation. I'd like to say thank you to everyone who joined us as well. The presentation slides and recording will be made available on our Bright Talk channel. We hope you have a great rest of your day.
Thank you, Patrick. Thanks, guys. Thanks, guys, for being the audience.